Welcome, everyone. This is Introduction to SparkView, and over the course of the next 60 minutes, I'm excited to be able to show you some of the fundamental approaches to using SparkView software in the education classroom to collect and analyze data, primarily from Pasco sensors. We have 3 activities planned today to accomplish that. The first one will be a quick introduction to a reaction between antacid and juice, as you can see on the screen. In that, we'll be learning how to connect sensors, look at measurements from those sensors, and do a little bit of visualization of those measurements, and perhaps a bit of analysis of the results. Then we're going to move on to a forces in motion, where we're going to take more control over the types of measurements we can get from the sensor and how we can display them in more complex ways in displays like the graph. And finally, we're going to do an activity where we investigate what a factor contributing to global sea level change might be. And for that, we're going to take full control over the way that we collect and visualize data, and we're going to use a different technique for gathering that data that's appropriate for that particular investigation. We'll take some breaks throughout. Barbara will kindly be answering your questions from the Q&A throughout, but we will also stop to talk about how we can share and save things in SparkView, what platforms SparkView is supported on, how to use various sensor families, and some resources for getting some experiments, student-ready experiments from Pasco. So let's begin with a quick demonstration. Let's forget about the sensors for a moment. And on the live screen there, by the way, if you're joining us live, you have the ability to change the relative size of my shared screen and the live video feed. So you might want to expand the video feed here. I have some cranberry juice in a beaker, about 75 milliliters. And I have an antacid tablet. This is an Alka-Seltzer antacid tablet. Sometimes called an effervescent antacid tablet. So I'm going to drop this Alka-Seltzer in the beaker of cranberry juice, and I'd just like you to watch the reaction and maybe record your observations, any questions you might have, and maybe even some ideas for investigation. And if you're with us live, you're welcome to put those observations and thoughts and ideas in the chat. So let me go ahead and just drop that in there. We welcome your feedback in the chat. What are you seeing? What are you thinking? Besides your observations, what questions do you have? What are you curious about? Do you have any ideas for things we can investigate? All right, Francisco, David, thank you. Bubbles, yep, lots of bubbles. Hua Young says gases, yeah, evidence. Lots of bubbles. Barbara here is close, she can hear fizzing. David, great question. Where did the bubbles come from? All right, energy, Andrea. Yeah, what could we measure using a sensor? I think Andrea knows where this is going to go eventually. What sort of investigations might you be curious about? Whether with a sensor or not. David asks, where did the bubbles come from? Fantastic. All right, seems to be dying down there. So let's proceed. Thanks for your observations and questions. So this is something about SparkView, a session on SparkView and sensors. So we are indeed going to take some measurements. But I have some sensors on hand here. Here's a list of some of the sensors I have on hand. pH, temperature, pressure, force and acceleration, CO2. What are some of the things that you might be interested in measuring with these? So if you have a question that could potentially be measured with one of these sensors, feel free to share that in the chat. While I wait for those questions, just so you know, there are over 30 wireless sensors in the line of Pasco's wireless sensors, measuring everything from physics to chemistry, biology measurements, earth science. And Barbara's kindly put a link there to the sensors. And if you're not using wireless sensors, you may have sensors from 5, 10, 15, 20, 30 years ago. SparkView still supports all those sensors, whether they're white, like our current line of wireless sensors, blue from Passport, or black from Science Workshop line from the last millennium. So thanks for your questions. Darren asks, is this exothermic or endothermic? Yeah, that's a question we might be able to address with the wireless temperature sensor. Mamta says CO2 wireless. Yep. Francisco asks CO2 detector. Christian shares, I recently carried out research with my students on how temperature affects the decomposition kinetics of Alka-Seltzer tablet. Yeah, a more advanced thing. If we change the temperature of the liquid itself, would that be something that we could analyze the effects of? Jackie asked, does the pressure change? Does the temperature change? Indeed. So we have lots of possible questions here. You may be asking, we have a CO2 sensor. Could we trap this gas and measure it? That's something we could do if we did this reaction in something like a bottle. Pull out here. If we did this in a bottle, we could potentially put the wireless CO2 sensor in the bottle and monitor whether this is CO2 coming off, as some people suspect it is, or not. So that's one thing we could measure. Lots of suggestions about endothermic, exothermic. Jackie asks about pressure change. We could similarly seal that up with a wireless pressure sensor. And as long as we had a closed vessel with either wireless pressure or the wireless CO2, we could take a look at the changes in pressure or CO2 levels. So something about the gases evolving. I think we're going to definitely do something with the suggestion endothermic and exothermic. So for that, we have a wireless temperature sensor. We'll use that to see if this indeed involves some sort of temperature change. Feels a little bit cool to the touch, but I'm not sure if my hands are sensitive enough to detect that. Francisco asks, how do we need to put the sensor if we want to measure the pressure increment? Indeed. So it happens that a lot of our sensors come with these 250 milliliter sampling bottles. So we could put the juice inside the sampling bottle, and we could quickly grab the pressure sensor. And before we put the antacid into the pressure sensor, we could take something like a one-hole stopper and fit the one-hole stopper into this bottle. And the wireless pressure sensor comes with tubing that we could use to connect it and seal this. I wouldn't recommend, the nice thing about the one-hole stopper is that it'll get a pretty good seal, but it won't allow dangerous levels of pressure because eventually that one-hole stopper will pop off. So to illustrate what I'm talking about there, I don't have the tubing at hand, but we could seal this with a one-hole stopper, use the tubing and connectors that come with the wireless pressure sensor and make that connection. Thanks for asking. All right. If you need to change the relative size of the live video and the screen, there should be a handle that allows you to do that. All right, Barbara has another suggestion there. Thank you for putting in a Ziploc bag. Let's go ahead and measure two things at least. We have a lot of opportunities here. I'm going to keep the reaction in this open beaker. That necessarily constrains us to not really trapping the gases. But let me grab a different beaker with the same amount of juice in it, and I'll grab another antacid tablet. The question I have is something about antacid here. If this is called antacid, is it going to change the pH of this solution of juice when we add the antacid tablet? So let's take a look at two things at a time. Let's take a look at pH, popular sensor of biology and chemistry, and temperature used across all the sciences. So to use the pH sensor, it comes in a storage bottle to keep the electrode working. So I'm going to take off this little bottle and I'll rinse off the storage solution. And then with a paper towel rather, tap it dry. And one trick about using the wireless pH sensor is it has this little cap. I'm just going to push that up so we can put the electrode inside the solution. Temperature sensor much easier. I just put the stainless steel probe where the temperature is measured about a millimeter or two from the tip. And we have those two sensors now in the solution. Now, of course, these sensors don't have displays. We have sensors with displays. These are not those sensors. So we need some way to visualize our data, perhaps display it, analyze it. And the answer there is, of course, SparkView. So let's go ahead and explore this reaction using at least two sensors, the wireless temperature sensor and the wireless pH sensor in SparkView software. So I'm going to launch SparkView. I happen to be on a Windows machine, but as we'll talk about shortly, SparkView is going to behave pretty much the same across all the platforms that you may have in your science classroom. When we open SparkView, it goes to the welcome screen where we're allowed to choose a path. And there are some popular paths, ways to use SparkView. Your eyes may be drawn here to the fact that we have sensors and there's a big sensor data path, and it tells us this is how we can connect our sensors, choose measurements and displays. That sounds perfect. And when you're doing your own investigation, that's often a fantastic way to start. So go ahead and choose the sensor data path. And basically, it gives me the opportunity to power on my wireless sensors. So each wireless sensor has a power button on it, built-in battery. I'm going to turn on both of my sensors, wireless pH and wireless temperature. And because I'm using SparkView on a regular computer with it fully installed, SparkView goes out and is actively seeking the wireless signal, the wireless Bluetooth low energy signal from any local Pasco sensors that are on. And it's found quite a few sensors around me. I have sensors elsewhere in the room, through the wall, maybe getting the sensors of my neighbors. So we need to figure out which sensors are mine that I want to connect to SparkView. So my wireless pH sensor, there's only one showing up here, but I can always confirm it's mine by looking at the 6-digit ID, which appears on the sensor case itself and should correspond to the same 6 digits shown in SparkView. So go ahead and click on that to connect it. It's going to make a Bluetooth low energy connection. And once it's connected, it shows up here in the center of this screen. We'll get to that in a second. This pH sensor, I should note, is no longer available for anyone else to connect to. So if Barbara was doing a similar experiment, Barbara would need her own wireless pH sensor. She couldn't connect via Bluetooth to mine. However, that doesn't mean I can't connect more sensors to do further investigations on my computer. So a sensor can only be connected by a Bluetooth to one computer at a time, but a computer can connect to multiple sensors for investigations like this one. So with my temperature sensor on, I see that its ID is 622-484 on the case. It happens to be at the top of the remaining list of sensors because it's giving us the strongest signal. So I'll tap on that, and I'll also connect the wireless temperature sensor to my SparkView program. All right. I didn't mention it before, but before I connected the sensors, the Bluetooth light was blinking red on the sensor case. Probably difficult to see in the video feed, but once I've connected, it begins blinking green. That's a nice way to troubleshoot so that you can make sure, is this sensor connected or not? Simply look at its Bluetooth light to see if it's blinking red or green. Now that I have my sensors connected, you'll see that they show up here in this list that says select measurements for templates. The pH sensor offers a number of measurements for using ion selective electrodes or things that produce voltage, electrodes that produce voltage. I'm going to stick with the pH measurement since I have the pH electrode that comes with it connected. The temperature sensor just offers one measurement, temperature. And what we do in the center column is basically say, well, what do I want to look at first? In this case, I want to keep things simple. For many of you, this is the first introduction to SparkView. So I'm actually going to uncheck temperature here. Rest assured, it's going to be collected. We can look at it later, but this is just saying, what do you want to look at right now? I want to look at pH first. I want to collect temperature, but I don't want to look at it yet. So with pH selected in the measurements for use with templates, we'll go to those templates in the upper right, and we can choose to look at the selected or checked measurement in a variety of templates from a graph to a table and a graph, digits and graph. I'm going to choose digits and graph, and it's going to look here and see that pH is checked and give me the requested displays of pH. So on the left side, I see a big digital display of the current pH value once I start data collection. And I see a graph of pH on the y-axis versus time on the x-axis. All new measurements and graphs default to showing time. It's appropriate in this case. We're going to see later in other investigations that we can choose other measurements on the x-axis as well. Now, if I'm interested in knowing, well, is my pH reasonable before I start collecting data, I can look down to the lower left and I can see what's called the live data bar. You'll see that the pH current value is being measured here. It's not being recorded, but I can see that the current reading is about 3.22. So this juice is indeed fairly acidic. That sounds like a reasonable value for that. So I can have confidence that I can proceed to collect data, knowing that I'm getting a reasonable pH value by looking at the live data bar. So how do we actually tell SparkView we want to record data? That's the job of the green start button on the bottom bar here. So I'll press start, and I will see a live digits reading of the current value here in the digits display on the left. And more interestingly, I'm going to see a display on the right of the evolution of the pH measurements over time, where each of those dots is a pH value that's being recorded into SparkView, connected by default by these straight lines. So I can see the pH in the graph is fairly level at about 3.2. You'll notice the graph automatically rescales itself by default to ensure all the data points are visible. I'll just simply put the Alka-Seltzer tablet into the juice, and let's see if we detect any change in pH from either the digits display on the left or the pH or the graph display on the right. Share your observations if you wish in the chat, or any surprises. Is this what you expected? This is an Alka-Seltzer Antacid tablet. Does it seem to be doing at least that part of its job? Now, we've already noted that the graph itself is scaling the axes automatically so that all the data is visible. I can also take control of how this graph is scaling. One of the things I can do is simply click and drag by default in the middle of the graph, and I can pan this graph around as if it's a sheet of traditional graph paper on the tabletop. Something I can't do with a traditional sheet of graph paper is I can click and drag on the axis number labels, either the y-axis or the x-axis, and you notice it's shrinking and expanding the graph as if it's made of rubber. So through a combination of moving in the middle of the graph and scaling on the graph axes, you can get the view of the data that you want. Now, it's often the case that you simply want to fill the graph space with the data to better visualize it. And if you want to do that, you don't need to necessarily manually do all those adjustments because there's something called the graph toolbar. I've collapsed it earlier, but if I simply tap on this single graph button, the single button that's at the bottom of the graph, you'll see it opens and collapses a tray of what we call graph tools. And the leftmost tool there, if I hover over it, is called scale to fit. When you press scale to fit, whether it's during data collection or after data collection, we see that the graph automatically scales the axes and pans around automatically to ensure that I'm seeing all the data. Jackie and Chantel, yep, notice that it is indeed making it less acidic. Going toward neutralization here, it looks like 6.4. pH is definitely increasing. So let's let that level off for a moment. And then what are some questions we might want to ask about the data that we see in the graph? Looks like it's leveled off fairly well. So when I'm done collecting all the data I want for a particular run, as we call it, I'm going to go and press the red stop button. And all the data we collected between the pressing start at time 0, experiment time 0, and stop at the end of the experiment comprises a run of data. And we can see from the graph legend that it's called run number 1 by default, and it has a unique symbol and color. Yeah, Barbara asked the question there, what's the rate of change at the start of the reaction compared to the end of the reaction? We might even start with the observation from Chantal that pH is increasing. So before we even do some analysis on the graph, let me go ahead and remind myself, well, what actually caused this change? One of the tools that we can use to label points in our graph is called the annotation tool. And if you hover over this letter T tool, you'll see that the tooltip tells us this is add annotation. The way the annotation tool works is it allows us to label a particular data point in our graph. So I'll click the annotation button, it pops open a screen, and I'm going to note here that I added an antacid tablet to juice. Now, by default, when I press OK, it's going to drop this tool somewhere in the middle of my graph, but I can grab this gray box and notice that I can drop it anywhere near a data point, a different data point, and it will snap to that. So I think right about there is when I added antacid to the juice, and I can move the label around here to make sure it's clearly visible. Chantal noticed the pH is increasing. That begs the question. So what was the pH at the beginning? What was it at the end? We can, of course, use our graph reading skills to see it went from something like 3.2 to 6.5 something. But as you can imagine, there are some tools here in SparkView's graph that allows us to do an analysis a little more precisely. One of those tools is called the coordinates tool. If you click on the coordinates tool, it acts much like the annotation tool, except instead of an annotation that you can change, it now tells you the coordinates of the data point itself. So this gray box, wherever I drop it, I can see is at 29.2 seconds, the x coordinate, and 3.22, that's pH units, unitless, for the y variable. Now, if I want to find the change, I could naturally go over to the end and add a second coordinates tool. I could move one or I could have a second one, and I can see that in the end it was about 6.55. I could calculate that change, but since change is something that we calculate across the sciences, there is a little shortcut. I'm going to delete my second coordinates tool by clicking on its label and choosing the X, because there's a hidden tool you're not going to find in the graph toolbar, but if you click on the coordinates tool label, you'll see this gray button looks like the Greek letter delta. This is the delta tool. And if you turn on a delta tool, which is hidden inside a coordinates tool, you'll see that it gives me a second handle, and I can drag out this second handle and drop it on another data point of interest. And now this delta tool, as we call it, hidden inside the coordinates, is now telling us the change in time, that is the x variable from here to here, was 146.6 seconds, and the change in y, that is the change in pH, was a positive 3.3. All right. So Christian talked about doing experiments with students about maybe changing the temperature of the juice. And in that case, you might be interested in time. How long did it take for it to stabilize? Does that change with the temperature? And questions like that. So the delta tool is a great way to figure out changes from point to point. And again, it's hidden inside the coordinates tool. So click on the coordinates tool label. You'll see that delta symbol. All right. Barbara asked a question about rates of change. She noticed that the rate of pH change seems faster at the beginning here and slower at the end. So that raises another question. Can we get rates from our data? And one of the ways we can look at rates is to make a linear fit to our data. So there's a tool here that analyzes multiple data points instead of something like the coordinates tool that analyzes single data points at a time. So I'm going to turn on linear fit, and it's going to do its best to try to draw the best linear regression line to all the data I've collected in this run. But that's not really Barbara's question. Barbara was asking, can we compare the rate at the beginning and end? And the answer is yes, we can. By default, these tools like linear fit apply to the entire data set, but we can restrict their analysis to sets of data points within the run. The way we do that is to recognize that by default, our cursor is a mover, but we can switch that. The reason it moves by default is this switch is set to move mode. If I switch it over to select mode, I can now draw a box with my cursor, and notice that all the data points inside that box are highlighted yellow, and that linear fit updates live to analyze only those data points inside the box. I can move the box. I can adjust the size of the box by grabbing these handles. And to answer Barbara's question, here at the beginning, it looks like our rate of pH change was the slope m 0.09. It would be pH units per second. And I can grab this and go later in the run and see that toward the end, it was a much lower rate of change of pH, 0.005006 pH units per second. All right, great. So that's a quick introduction to connecting sensors and visualizing the data, especially in a graph display, and some of the key things for doing data analysis in the graph. Sometimes we use tools like the coordinates that analyze points, and at other times we analyze either entire runs with something like linear fit or turn on selection mode to change which data points we're actually analyzing. Now, you'll recall that many of you had questions about temperature. Was this endothermic and exothermic? And even though I didn't show the temperature when I chose to set up this experiment for the sake of simplicity, we can look at temperature as well. I could simply go over to the y-axis of my graph, click on it, and change that to, say, the temperature measurement. If I did that, though, I'm going to lose my analysis. So I'm going to just remain here in this graph. And what we can do in a graph is we can add what's called multiple plot areas. So down here in the graph toolbar, there's a button that says Add Plot Area. I'm going to click on this, and it looks like it adds another graph. It adds what SparkView calls a different plot area. I'm going to change the measurement on the y-axis here to temperature, and here's our temperature over time. The reason these are called plot areas is they share a time axis. So notice as I scale the time axis of the lower plot area, the top plot area's time axis scales as well. So these are nice and linked, and we can see these changes in pH versus time on the top plot area and temperature versus time on the bottom plot area at the same time. Now, one more key thing here is you may be interested in asking, well, what was the change in temperature? And you've already learned that the coordinates tool is a great tool for analyzing that. But let me show you a little thing you have to learn when you have more complex graphs like this in SparkView. You have to learn that there's only one graph toolbar. And if you turn on something like the coordinates tool, you don't know necessarily which plot area it's going to apply to. So there's one more trick to learn here, and that is notice that in our graph legend, it's a shared legend between these two plot areas. Only one of the measurements, in this case Y1, the pH measurement, is active, as indicated by this red square. If I want to actually use the tools, the analysis tools on the other measurement, I simply click on it to make it active. And now I can turn on coordinates tool for the temperature or lower plot area and do something like reveal the delta tool to figure out that it indeed was endothermic, and looks like the temperature decreased about 1.1 degrees Celsius. All right, so some key ideas, knowing all the sensors that are available just with these techniques of connecting a sensor, choosing a display, and doing quick data collection and analysis. Think of the range of experiments you can do with 30 plus sensors that you may have in your classroom. Barbara, any questions that we should address as a group before we continue on? Nope, good. All right, thanks. I see questions coming in there. Thanks for those. So once you do an investigation, you oftentimes want to share the results or record them for posterity. So we're going to talk throughout our webinar today about different ways that we can save and share data from SparkView. The first and most fundamental way is to simply save the entire file in a proprietary format called a SparkLab file. You do need SparkView to open it, but it preserves everything about the file, from the displays to the settings for data collection to the analysis that you might have done on the data that was collected. But anyone with SparkView can open it. That includes across the platform. So if I save it on a Windows computer, I could send it to Barbara on a Mac or a Chromebook, and it will open just fine as long as the recipient has SparkView. So let's see how we can save a SparkView file. I'm going to go to the main menu in SparkView, the hamburger menu in the upper left, and choose Save. And since it's the first time I've saved, it's asking me to give it a file. Here you can see that it is a .spklab SparkLab file. So I'll call this antacid in juice data. Hit save. I'm going to close SparkView just to prove that it saved everything about it and show you that we can then open a file, a SparkLab file, from SparkView's main menu. So I'll relaunch SparkView. And we have this option to open a saved experiment. This will direct you to open just experiments that have the SparkLab extension. I can press open for the file I just saved. Again, this could be on a different computer, and you'll see it preserved everything about that file. So the most complete way to save a file, to preserve it, is to save it as a SparkLab file using the main menu. Stephanie asks a very timely question. Will it save your files if you're using an iPad? The answer is yes. Um, Generally speaking, mobile devices like tablets and phones, they're increasingly having file systems, but they don't quite have the same robust file systems that computers have. So in that case, you're probably interested in this sharing button. And the sharing button that you'll find on an iPad, iPhone, Android tablet, Android phone, would allow you to essentially share the SparkLab file using the share sheets built into, in this case, iPad OS. And that would allow you to save the SparkLab file and share it to a Google Drive, email, message, whatever sharing techniques you use via the share sheets. Great question, Stephanie, and timely. Oh, okay. We've covered a couple of paths so far. The sensor data path is a great way to just ask a question about the world around us and to gather data using basic displays. We also saw that once we have a saved SparkView file, we can open it up via the open saved experiment. And we'll be taking a look at these paths, more of these paths as we go throughout today. So a little bit about SparkView software. Basically, we want SparkView software to be available on whatever computing devices you have in your classroom. So it's available on all of these: Windows, Mac OS, Chrome OS, iPad OS, iOS, Android, whether phone or tablet, and some of our own dedicated loggers. And it's available in two different forms. Traditionally, applications like SparkView are something you install or your IT folks install, depending on your rights. And for things like Windows and Macintosh computers, we have a licensed installer, a site license, or if you're a Pasco portal subscriber, it's included in that. Then we have free apps available in the app stores for iPad OS and iOS and Android. There used to be that there was a free app on the Chrome Web Store, but Google is sunsetting the Chrome Web Store. So the next version of SparkView that I'll show next is the solution on Chromebooks and on other platforms. So we have the ability to run SparkView in the Chrome or Edge browser by simply going to sparkview.pasco.com. So in the next activity, I'm going to run SparkView in the browser. There's only one key difference about SparkView run in the browser as compared to run as a native app. But once you've connected Sensor, which is that difference, we'll be able to see that everything else functions the same. There's a question here about if you're on a Chromebook. I'm going to do a Chromebook in the third activity, but basically when you save using the main menu in SparkView from the Chromebook, you will have all the same options you do for file management, from the downloads folder to, by default, the Google Drive folder that your students may have. All right. If you want to learn more about SparkView, you can go to pasco.com/SparkView, and note the difference there. Pasco.com/SparkView for more information about all forms of SparkView. If you want to use the progressive web app, as I will in the next activity, SparkView.pasco.com. All right, so for this next activity, we are going to take a look at another sensor. This doesn't look like the traditional white sensors of our wireless line, but it is indeed a sensor. But first, let's start with the science question here, and that is, how does an object respond to forces applied to it? All right, the object we're going to use is this smart cart that you can see in the live video feed. I've attached a hook to this, and this hook is how I'm going to interact and apply forces to the smart cart. And we're going to investigate, well, if I apply a force to the cart, say a push or a pull, how does its motion respond? And can we make some connections? And as promised, we're going to do this with the SparkView PWA, or progressive web app. I see you're sharing some great ideas there for Chromebook use. Thank you for doing that. All right, so if I'm going to use SparkView PWA, I need to open up a compatible browser on my Windows computer. That could be either the Edge browser or Chrome. So I'm going to open up Chrome. I'm going to go to that web address, sparkview.pasco.com. And Basically, it has downloaded some files into the browser. I didn't need to do an installation like I would with the native SparkView application. And I'm in my Chrome browser, and this pretty much looks like what you saw when I used the native version of SparkView. And as I promised, it's going to behave pretty much the same as well, with one important exception here. Once again, I'm going to take the sensor data path because I'm interested in making measurements from the smart cart that we have here on the track. And I'm going to go ahead and press sensor data. I will turn on the power to my smart cart, which is really just a suite of sensors on a low friction cart. And at this point, if I was in the native SparkView app, I just wait for it to show up. But because we're in a browser, the browser has to control the sensor connections via Bluetooth. So what we need to do, instead of just waiting for the sensor to show up, we need to take an action. And that action, as described here, is click the Bluetooth button to connect to a device. I'll click the Bluetooth button. And at this point, it's the browser saying, well, do you want to connect to something? It's a little more cryptic because we can't control how the browser does this, but fundamentally, you're going to see that the smart cart has an ID, just like the wireless temperature and pH sensors had an ID. It's printed on the cart, and that 6-digit ID is somewhere here in this little code. It's before the greater than sign. So I'll select that sensor, press pair, and it'll take a moment for the browser, but it's going to make a wireless Bluetooth connection, and then it's going to feed that connection into the SparkView PWA progressive web app running inside the browser. There we go. So from now on, everything's going to be the same, whether we're on the PWA or the native app, as we saw in the first activity. Now, as I said, the smart cart is a suite of sensors on a low friction cart. There are a lot of measurements available here. I don't want all of these. So if there's a measurement I'm not interested in making, that is from a sensor I'm not interested in, I can turn off that sensor. For example, I'm not interested in the 3 axes of acceleration, so I'm going to turn that off. I'm not interested in angular velocity from the gyroscope, so I'm going to turn that off. But I am interested in these measurements coming from the smart cart's position sensor, which is an encoder on the rolling wheels. And I am interested in forces because I want to see what happens to the motion when I apply forces. So I'm going to check all of those 4 measurements: position, velocity, and acceleration, and the force. All right. Now, what do I want to see it in? Well, I'm going to choose a graph display. I think that'd be great for visualizing these measurements over time. So with these 4 measurements selected, I'll choose graph like we did before, the graph template. And well, it turns out the graph doesn't want to get too busy. So it only showed me the first 3, but that same technique we used earlier, add a plot area, would allow me to add the 4th plot area. This is the limit just for screen real estate, but I now have plots of position, velocity, acceleration, and force versus time. And now we can begin exploring things like, well, what if I apply a net 0 newtons force to this cart? Well, you'll notice that the live data bar tells us that the force right now is not quite 0, even though I'm not pressing the hook, which is connected to the cart's force sensor. But we can 0 that by pressing this live data bar, which is actually a button, and I can choose to 0 that. So I'm now recording that as 0 newtons applied force. I'm going to press start, and well, not particularly exciting. No net force applied, no change in its motion, position, velocity, acceleration. All right, so that's one thing we can do. Now, before we go on to actually do interesting data collection, I'm going to go here in the control panel for sampling options, and I'm going to take a look at what we can do in terms of data collection. Every sensor has a default sample rate, which is reasonable for many applications, but from prior experience, I know I like to have a lot of data collected for this. So I'm going to say that across all the sensors, I'd like to increase the sample rate from a default of 20 measurements a second, it's 20 hertz, up to maybe 40 hertz. Also, because I'm going to be juggling a lot of things, I'm going to put a stop condition on here. And this stop condition, I'm going to say I just want 5 seconds of data because I have to go over here to the table to collect this data. So I'm going to have SparkView stop automatically. All right, so let's actually apply some forces. If I grab the hook, I can apply some forces here. I'm not going to grab the cart because that force wouldn't be measured, but let me go ahead and apply a positive force, positive as measured, as indicated by the axes on top of the cart. Go ahead and hit start, apply a positive force. Oh, sorry. Can take a little bit of a delay when we're in the PWA. So this time around, I'm going to press start and wait for the data to show up. Then pull it. So positive force. We can see gave us a positive change in position, positive velocity, positive acceleration. So we could apply a negative force and so on. But I'm interested in applying various forces and seeing maybe if one of these measurements of motion, position, velocity, acceleration correlates best with the forces I'm applying. So what I'm going to do in a moment is collect yet another run of data, and I'm going to grab the force sensor's hook, and I'm just going to move it back and forth sporadically here, but I want to push it and pull it with varying forces. And let's see what the graphs of position, velocity, time, and force position, velocity, acceleration, and force look like against time when I do that. All right, got my 5 seconds of data. And here, I welcome your observations. Does it seem like any of these correlate with each other better than any other pair? Again, we have position at the top, velocity, acceleration, and force. Do you see any correlations between any pairs of these measurements that we looked at? Feel free to share that in the chat. Here's another example of what it might look like. Data I collected earlier, which motion measurement correlates best with the applied force? Force is at the bottom. We have position, velocity, or acceleration. Yeah, Dale notes force and acceleration seem to line up both in this data I collected earlier and in the data we just collected. Notice where the bumps are. Emily uh, also thinks acceleration. Fantastic. So let's explore that a little bit more. And although I started the sensor data path here with just requesting a graph, and I let SparkView choose how to design the graph, whenever I have more questions in SparkView, I can say, you know what, give me another page. I want some more displays. And I can add a page using this new page button in the top bar. So I'm going to add a new page, and SparkView basically gives me control over how I'd like to lay this page out. I can select a layout along the right side. I'm going to choose a layout that's just a full screen item. And here I can choose a graph display again, but this time around, instead of having something versus time, I'm going to take your advice here and see if there really is a correlation here between acceleration on the y-axis, and I'm going to switch from time to force on the x-axis. I'm going to hide all the measurements I made earlier so that I can press start again and apply this force varying and see if it correlates to the resulting acceleration at all. All right, so there's my 5 seconds of data, scale to fit. Looks a little bit messy, but that's because those data points are connected one to the next in time. If I go into graph settings, I can turn off those connected lines, and I can see that, looks like there might be a linear relationship here between the y-axis variable acceleration and the x-axis variable force. And indeed, if I turn on a linear fit, it can tell me something mathematically about that relationship. Well, I took the sensor data path to kind of explore a little bit, but if you wanted to do a demonstration in class, it would be nice if this was already set up for you, wouldn't it? So to accomplish that, I'm going to go ahead and save this file. Notice I'm saving the file from PWA just as I did from the native app of SparkView. So this is acceleration versus force data. And I'm going to return in SparkView to the main menu here and choose sensor data path again, because with this smart cart connected, SparkView has a few tricks up its sleeve where it says, you know what, sometimes with the smart cart, you might want to do experiments in these categories. So instead of using the selection of measurements and templates, I can jump directly into what some of you have already stated in the chat there. Isn't this Newton's second law? Go to Newton's second law. And this is set up opposite what I had before, force versus acceleration, for reasons that you'll see later. But let me go ahead and collect some data. First, I need to zero the sensor because I'm in a new file. I can press start. And let me collect some data here of the smart cart. Again, now force on the y-axis and acceleration on the x. I can turn off these data points, or rather the lines. And I'm also going to turn off this behavior to show only current run when recording. And now I can apply a linear fit. And because of the way I have my axes here, it's force versus acceleration. And it turns out the units of that are kilograms. And it tells me the slope here is 0.253. Well, if we're talking about mass, wouldn't it be nice to maybe double the mass of the cart, which I'll do by adding a mass bar here. I'll press start and let me collect another run. If the slope represents mass, how should this be different from the first run? Press stop. I can do a linear fit to that as well, 0.499. This is about half a kilogram. I'll add 250 more grams. Press start, and you can see we can go through this illustration that indeed the item which connects force to acceleration is the mass of the object that we're accelerating with that force. All right, so you can see nicely we have essentially the slopes representing the mass of 250 grams for the card itself, 500 grams once we've doubled it, 750 grams once we've tripled it. All right. So let's talk about one more way to preserve information from SparkView. I'd probably want to save this file, which I'll do by saying save as Newton second data. I can always go back to it if I save it as a SparkLab file, but let's say I wanted to put this in a report. What's another way I could preserve this? Well, another thing we can do is take an image of a display and paste that into a document. Once again, on mobile devices, you'll find this in the sharing option. On other computing devices, it's usually quickest just to know the screenshot tool built into the operating system. Since I'm on Windows, I'm going to press Windows Shift S, but it works on Mac or Chrome, depending on the keyboard press you use. So Windows Shift S will allow me to take a screenshot. That goes to my clipboard, and now I could paste it into some sort of report, some lab report. If you use Word, you could paste it in here. All right, and adding some words to that. Here is my lab report with the exact graph. Now, this is a static image collected from SparkView, and that's why I always like to preserve the original in the form of the SparkLab. But if you want to just have an image of a display, especially a graph with analysis, remember the screenshot tool built into your operating system. All right. So those were examples of a demonstration version of Newton's second law. If you're interested in doing Newton's second law with your students, I just want you to know we have an entire experiment library with hundreds of labs. If you search Newton's second law in the experiment library at pasco.com/free labs, you'll find a handout ready for students to use. It uses a different technique because this requires a bit of finesse to push and pull, but it does a more constructive example of applying various forces and seeing the resulting acceleration. Those labs are going to have the students open up a file that's built into SparkView. So from the welcome screen in SparkView, the first step of that lab is going to tell them to open a particular file. Those files for this particular experiment are built into SparkView under Essential Physics, Newton's second law. And this is set up for them to begin collecting data to save them lab time at the beginning. Now, if you are a subscriber to Pasco Portal, or your school rather is through a subscription, we have that same lab and others in the Pasco Portal where we also add editable student files if you want to tweak it, teacher answer key, ability to transmit files via the LMS or including Google Classroom. But in either case, look at those experiment libraries either at pasco.com/free labs or in the portal to find experiments that are already across the grade levels in sciences that can use SparkView in your sensors. All right, and that was the open Pasco experiment path. So we have 15 minutes left together here. I want to do one last investigation here about the topic of sea level rise. So as I get set up, let me know in the chat, what mechanisms do you think might contribute to global sea level rise? And as we do this, I'll go ahead and show you what I'm going to set up as we wait for your responses there. What might be contributing to global sea level rise? As promised for this final activity, I'm going to be using a Chromebook. So let me bring up my Chromebook screen. All right, Christian, CO2 might be contributing. Darren, thermal expansion. All right. Any other thoughts? Yeah, temperature increased by CO2, air. All right, melting and polar ice caps. Yeah, generally the two big contributors there, roughly half and half, are melting of glaciers, polar ice caps, and thermal expansion. We're going to explore half of that. In this case, we're going to explore the thermal expansion part of it. So let me share my screen here so that you can see what's happening on the Chromebook. But bottom line is going to be that the Chromebook is going to behave pretty much like the other devices we've been using SparkView on. Because I'm going to be using a Chromebook, though, we have to use the PWA or Progressive Web app. All right. Sorry, still getting set up with that. There we go. All right, so here is my shared Chromebook screen. So since we're on a Chromebook, I'm simply going to open up my Chrome web browser, and I'm going to go to the PWA address, sparkview.pasco.com. And as we did in PWA, I'm simply going to choose sensor. Actually, in this case, let's take a little more control. As I set this up, let me ask one more question of you. Um, Here's a JPL lab that kind of inspired this. There's a student lab here for looking at the effect of water expansion, thermal expansion on sea level rise. The URL there will give you some more information. I kind of wanted to sensorize this, so I set it up, as you can see here on the live screen. And in this diagram, I have a vessel, a 500 milliliter Erlenmeyer flask full of water. I've added some food coloring to make it easier to see. And I put a temperature probe in this. You can see a close up there. And if the water indeed expands or contracts with temperature changes, I should be able to take a look at where the level of the water is in this little glass vial. So in the chat, share, what do you think we should measure if we're interested in this idea of thermal expansion? You might want something more concrete. What should our measurements be? What are we going to change and what will respond to it? What are our independent and dependent variables? What should we measure? Yeah, Maria thinks temperature, thermal expansion, temperature, Darren says level in the tube. Indeed. Yeah, we're definitely going to measure temperature. That's why I have a temperature sensor in that two-hole stopper on top of the flask. The other thing we're going to measure is something about expansion. And I like Darren's idea that the level in the tube is something we can very easily measure, right? We can view it. And indeed, I have a ruler behind that level in the tube to make it a little bit easier to make that measurement. So we have something new here, and that is we have one measurement coming from a sensor, temperature, and we have another measurement that we can just type in. That is the height of the liquid in that glass vial. So to do this, I'm going to go to Build New Experiment and take a little bit more control over how we're going to design this lab. I'll choose Build New Experiment. And like we saw with the building a page earlier, Build New Experiment allows me to create the layout that I want. In this case, I'm going to create a small thing on the left and a big thing on the right. And the small thing on the left is going to be a table because those are nice for typing things in. And the big thing on the right will be a graph of the things that we're collecting on the table. So what are the two things we want? Well, the suggestions there were temperature. So inside a lab, I can go to the Bluetooth button. And because I'm in the PWA, I'll turn on my temperature sensor that's in the vial or in the flask already and connect to it if I know the right ID, 136. Oh, sorry. So this is 779-136. So I'll connect to it. And hereafter, it doesn't matter if I'm in the PWA or not. I've connected my sensor, and I'd like to vary the temperature. So I'm going to put that on the left column of my table. Now, what do I want to measure? I liked the suggestion for our level of liquid. I'm just going to double click in there because as soon as SparkView knows that I want to type some things, it creates for me a data set called user data. And in this case, it's going to be the height. And this is something, as user data implies, something I'm going to enter. So I'll do that in centimeters. And then I'm going to do the height as user enter data on the y-axis and temperature from the sensor on the x-axis of my graph. Now I'm almost ready. The only other thing to note is that if I just press start, it's going to collect data at 2 hertz, 2 times a second, which is in no way enough time for me to figure out what the height of that column is and to type it in. So I'm going to go to the sampling options once again, and I'm going to switch it over to this mode called manual. As the name implies, manual lets me control manually when I'm going to collect data. All right. So with it in manual sampling, I am now almost ready to take a look at these measurements. And just so you can see what I'm doing, I am going to be reading off the level of the water along this ruler. And you can see the little blue die here allows me to see that level. And I'm going to be increasing the temperature of this by placing it on a heater stir. I'm going to stir the water to make sure that temperature changes equilibrate pretty quickly. And then we'll just take a look at how I can collect data in this manual sampling mode. So I'm going to go ahead and press start. And as before, all the data I collect between pressing start and stop is a run of data, but now notice that no data is being recorded until I command it to using that green check marks, which is called keep. So I can see the current temperature is 7. I'm going to go ahead and look at the level, and I can see that it is at 10.95 centimeters. So I'll correct that first value. And I'll press keep. And now that data point is recorded, that pair of temperature 7, height 10.95. I'm going to turn on the hot plate in this hot plate stir. And this change in height of that water level in the tube was going to happen fairly quickly, but I'll give it a moment here to begin rising as the hot plate begins turning up. And the thing to know here is that in this manual sampling technique, you are in control of when the sensor data points are collected by hitting the green check mark for keep, and allows you to type in a corresponding real world measurement, in this case, the height. So we can see the temperature is beginning to rise here, and looks like the water level's actually fallen a little bit, so I'll give it a moment to get a little bit warmer. Sometimes the jostling around will cause the water levels to change a little bit. But if you ever want to correct something, you can go back up to a data point and click on its cell, and you can correct it. So if I now see the water level, now it looks like it's approaching 11.00. I'm going to wait until it is 11.00 and press the keep button and fix that. And we'll really crank up the heat here since we have only a few minutes left. But for each of these data points that I keep, it's plotted in the corresponding graph. And ultimately, we want to see if we can find a relationship between the height of the water and the corresponding temperature. Barbara, any questions as we wait for that to heat up a bit?
Not so far. Go ahead and
Okay.
enter your questions in chat if you have any, please.
You can see that the water level is rising slowly here. My experience is with the hot plate on high, it's going to go quite rapidly. All right, so it's approaching 11.5. Sometimes it goes so rapidly, it's a bit tough to get. So I'm going to wait until it's at 11.5 right now and press keep. And now we have our 2 data points. Perfect linear relationship. So this manual sampling technique is great if you want to correlate a sensor measurement with something from the real world, whether it's measured off a ruler or off of a volumetric measurement like a burette for a titration. I'm at 12 now, so I'm going to press keep at 12 centimeters. We'll get a couple more data points here. While we're waiting for that to go up, you might be able to see it's rising visibly now in the live camera feed. Getting close to 12.5. One thing that's important for students to know when they are doing manual sampling is that we're not pressing stop until we've collected all the individual data points that we want. If we press stop, we would only have these data points in the run, since start and stop is collecting data from the beginning to the end of the run. All right, approaching 13. Let us know if you have any questions. There's 13, so I'll keep again. And we can see it's maybe not quite linear. I'm going to let it go a little bit more since we're nearing the end of our time. Let me wrap some things up and then we'll return to this data. What we're doing here in manual sampling mode is in contrast to the periodic sampling, which is the default, where we press start and it collects data at a fixed sample rate defined, fixed rate defined by the sample rate. In the case of the manual sampling, we're pressing start, and then we have all the time we want in order to decide which data points we want to keep. And in each case, we have the opportunity to correlate it with particular measurement. Getting back to here, we're going up to 14.2 now. We'll collect a couple more there as we wrap up the presentation. One more thing we can do is export data from SparkView to open in a shared spreadsheet program. And that works whether you have sensor data or user entered data. It's not something you use very often, but if you just want to use SparkView to collect data from a sensor and bring it into something like Excel or Google Sheets or collaborate with other groups, know that you can also export data. And that's also in the main menu of SparkView or on phones and tablets in the sharing menu. So build path allows us to take more control. I'm going to wrap up and say that we will continue the recording if you want to see what this data looks like and do a little bit of analysis. But if you need to leave, one thing that I want to leave you with is a couple of resources. One thing that's useful to know is that SparkView has an extensive help system at help.pasco.com/SparkView. And this is a great way to learn more about particular features. We've covered some core features of data collection today in analysis, but if you want to dive deeper or answer your questions, help is a great way to do so. If you want to help your students get started this semester with SparkView, we have a tutorial video. It's about 10 minutes long, and it introduces kind of the core features of SparkView in a very concise way. And I'll ask Barbara to share that in the chat. And then if you're a portal subscriber, we have a whole course on SparkView. You can get a certificate. It's a few hours long and really dives down into different approaches to using SparkView in the classroom with education labs. All right, if you have any questions beyond those that are answered on our website, though, don't hesitate to contact your local Pasco rep in the US or across the world at pasco.com/support. And with that, I will end the formal part of this, but we'll collect a few more data points if you're able to stick with us. If you need to leave right now, thank you so much for being with us today. And as you leave, it's going to give you the opportunity to do a quick survey. We appreciate your feedback on what went well today and what we can improve. In the meantime, let me go ahead and collect a couple more data points. If you have a couple minutes, we'll collect a few more and take a look at this relationship between the thermal expansion and the temperature. All right, so let me do one more data point. I will press keep, and we are all the way up to 18.3. Give us a good clue as to whether it's linear or not. Not yet linear. So let me go ahead and press stop. All the data we collected comprises a run. So we have those 7 correlated pairs. And now if I zoom out a little bit, we'll see that it's definitely not a linear relationship. So SparkView offers linear fits, but it also offers nonlinear fits in the form of this fit toolbar. When in doubt, choose a polynomial. So I'm going to choose a quadratic fit. And we can see it describes some sort of relationship between the height of the water, in this case representing a proxy for volume, and the temperature. And if you're a fan of water, you may be curious to see that it doesn't look linear. And indeed, you might ask yourself, well, what's the densest temperature for water? And it looks like our curve fit here is revealed to be around 4 degrees Celsius, which is indeed a property of water, a unique property of water, that it's densest at 4 degrees Celsius. So quick investigation there, introducing the idea of manual sampling and designing your own labs through the build path.